All right, so this is going to be another use case, this time of the PLL in the electric vehicles. So now in the electric vehicles, it is also um, quite an upcoming feature in the electric vehicles that they have a bidirectional energy flow, which means your vehicle can also act as a vehicle to home, or vehicle to load, or as a vehicle to grid. So what does it mean? So when you have, let's say, a vehicle, an electric vehicle, or at least a plug-in hybrid vehicle, and you have this little charge inlet, and from this charge inlet, you go to something called as a wall box, home wall box, and from the wall box, you are connected to the grid, right? So what generally happens during charging? It is straightforward. You are taking the AC and converting it into the DC, and you are charging your battery. Absolutely nothing to talk about in terms of the phase lock loop, right? So it is as simple as you're getting an AC signal. So that AC signal passes through first level, something called as a PFC. I have made an entire course on this. You can also check out what is this PFC on my course page. And from the PFC, um, you will have basically a DC link. So you will, yeah, basically the output of it would be a DC voltage. And from the DC voltage, you again put it back to an inverter phase wherein you are putting it to a high frequency AC signal. And that high frequency AC signal is again being put back into a transformer, and you again have a kind of a power electronic here, and the power electronic finally is given to the battery, the HV battery, which is here, which is maybe 400 volt or 800 volt or whatever it is. Now this is all for charging, and when you have the discharging, what happens that you take energy from the battery of your vehicle, you put through the same power electronic to convert it into AC, put through this transformer for the galvanic isolation, put it through this DC link, and then instead of doing a power factor conversion, you do the inversion. Basically, you are doing the inverter functions. Here is where you will have now the PLL implemented. So that means through this inlet side, you are looking into what the grid is doing, and the PLL is integrated into the power electronic of the so-called PFC stage. So it's no longer a PFC because PFC is only done during charging, but inverter operations are done during discharging. So this PLL sits here in this PFC, and then it is going to feed the energy. So there's going to be a current controller. So why there's a current controller is always because, so if you have a grid with certain voltage, and if you want to feed that grid, your voltage should be slightly higher. Only then you can only then you can start to feed energy into the grid. So basically, if you want to feed 3 kilowatts, so you are always having a current controller. You will see that based on the grid impedance or the impedance from the point of common coupling all the way to the to your socket. So you will have to have a current controller, which is ensuring that you are changing your voltage set points such that um, the the differential current which is going into the grid is dependent on your grid impedance. Basically, it's a simple thing that your VOBC, right, minus the V at the point of common coupling. So VPCC is nothing but your, this is going to be I, which is your current which is coming out of your OBC multiplied by the impedance. So you always have to have an OBC which is giving you a higher voltage than the voltage at the point of common coupling, which is given by I multiplied by Z. So this is all done, and the PLL is also useful, greatly useful in the OBCs of electric vehicles which are supporting bidirectional energy flow. So that would be all, and hopefully you like the course, and yeah, thank you.